things started, that way we don't miss anything. So I have up the course webpage to point out a couple of things. Number one, I don't know what day it was, but recently I made a video, maybe last Wednesday? That sounds about right. It's just a short demonstration of how to use M+ within the virtual desktop. So if you've never used virtual desktop before, or you've never used M+ before, this will help you just get acquainted with how the package works. It's really straightforward. I have example files that go with it. I have a handout on how to get into the virtual desktop and find your stuff if you haven't had to do that before. And then I added a couple of things to lecture 4. I sent out an email, I think, on Sunday. I annotated a couple slides, and I added a new slide 78. So the new version is posted. That is posted where it was last week, so there's only one version that's posted at a time. And then the stuff for today, there is a handout for example 4, which is a combined PDF of code and output and all of my annotations. There is a spreadsheet that demonstrates a bunch of different calculations. And then there is a zip folder that has all of the original files using M+ and R, input and output, but not data. These are real data, and I don't have permission to share them, but you can look at the full input and output. And then last but not least, back when, so Jonathan and I both taught SEM at KU, and the course was cross-listed with each other because we were in different departments. And so he took, our materials have quite a bit of overlap because I borrowed his slides and then he borrowed my slides, and we just sort of made it into one thing. But I have the full Levon version of everything that's in my handout posted here for your reference if you want to know how to do all the stuff in R. So I tend to rely on Excel for example calculations because it's transparent and everyone can use Excel. But if you want to learn how to do ggplot2 and all the other stuff inside R to make pictures, there you go. So just wanted to make sure that everyone was aware of all of those different resources posted under different links here. Any questions about that? Okay, so today we have formative assessment number 1 to go over. A week from yesterday, your first homework is due. So instrument background, it's a Word document. When you click this link, you can type in it. Type in it and send it to me. That's my intent. And I've spoken to several of you about what data you want to use. So the idea, the most important thing is that I want these assignments to be useful. I want this to be an examination of a scale that you use in your research or care about or otherwise would benefit you to know these things. So if it's a scale that exists already and you're just using it, that's fine. If it's a scale that didn't exist up to this point and you made it, so you don't have an article or something, that's fine too. That might actually be better because then you have all this new stuff that you can do that hasn't been done before. If you are in neither of those categories, if you don't work with people who collect data that you can play with, then I want to remind you that on the very first lecture 1, this is lecture 1, slide 10, I have links to 2 different archives that have item level data that you can peruse and see if you can find something that speaks to you. But the key idea is that you should eventually have item level data that you can play with for the remaining assignments using your individual data. Homework 1 then would be doing the background check as to what has been done with respect to psychometrics of these data and answering the questions about it. So let me know if you don't have data or this doesn't work for you. There's lots and lots of data on the internet from other places that you may be able to find. Again, my primary concern is that this is a useful exercise. So if you have something and you're not sure if it's going to work, just let me know and we'll talk about it. Okay? Does everybody have a sense of what they're going to do, maybe? A loose sense to get started? Yeah. So homework 1 should not take very long. It requires you to read an article or 2 at most and answer some questions. And there is a spot to submit it inside Icon already. And so that will be where it goes. Then, oh, that's right, I forgot. And I also posted your next formative assessment for the week after that. So if you're somebody who likes to get things done early, what we're talking about in class this week will be the topic of the next formative assessment. So after we get through this material, you should be able to answer those questions as well. All right. Any questions on any of that? Scheduling, logistics, etc.? Copacetic? Reasonably so? All right. Then I will shut that one. Shut that one. And we have some questions to go over for formative assessment number 1. Making sure I'm recording. Yes, I am. Very good. So I had a chance to read through all of your answers this morning and update grades. I also had a chance to gather all of your theme songs. So thank you for playing along. I built a YouTube playlist and I posted a link to it as an announcement inside Icon. So if you'd like to get a flavor of what other folks have selected for their theme songs this semester, it's always entertaining to me to see the different things that people select. Several of you who are in both classes that I'm teaching picked the same song, and that's fine. I decided I was going with a different one this semester for each class. So for longitudinal, my theme song is going to be Runnin' Down a Dream by Tom Petty. For this class, it's Uptown Funk. I know, you might be tired of it, but I've recently discovered or rediscovered how much I love that song. And I also mean it as a response to Reviewer 3 for a paper I'm currently helping get through the review process, who's fighting with me about the use of IRT versus CFA. And I want to tell Reviewer 3, don't believe me? Just watch. So that's my theme song for right now. They have the audacity to tell me that IRT and CFA are nested models. I'm like, no, they're not. I know. So don't believe me? Just watch, because math don't care. But, anywho. So yeah, on that note, please help me school Reviewer 3. What dictates whether you would choose a confirmatory factor analysis, an IRT model, item response theory, or some other model that doesn't really have a name but might be called generalized? What is the deciding factor? Yeah, what kind of data you're predicting. It is exactly the same as what kind of regression model do I need. If you have responses that are plausibly continuous and normally distributed, that's what CFA is for. If you have binary responses, that's what IRT is for. If you have ordinal or nominal responses, that is what polytomous IRT is for. And what if you have like a count? You can do it. It doesn't have a name. I just call it generalized latent variable modeling. What if you have a zero inflated negative binomial? Can you do that? Sure you can. You can do whatever you want. Can you mix and match? Can you have a latent variable that is measured by a binary outcome, a continuous outcome, an ordinal outcome, and a nominal outcome? Could you do that? Sure you can. It's a little tricky with the software and it's non-traditional, but absolutely you can. So yeah, think of it as just, it's like Mr. Potato Head, right? You have like the pieces that fit into the different parts of the toy and you just have to figure out which piece fits in based on what you're trying to do. So yeah, there are differences in terms of how difficult it is to estimate these models. That is certainly true, and we'll get into more of those details as the semester progresses. But yeah, this is the big distinction is what kind of outcome are you predicting? In all of these choices, what are we saying about the latent variable, though? What kind is it? Continuous and normal. So they all have that in common. As we will see, though, whether your latent trait distribution is actually normal is going to be dictated by what kind of items you have and where they contain information. You may very well end up with a non-normal theta distribution or latent trait distribution because you don't have enough information, particularly for scales that don't have a lot of items. Okay. Any questions or comments, clarifications on that first one? Cool.
I have a question.
Hit me.
Not actually about the quiz, but sort of about the quiz.
Okay.
Did you and Jonathan write your quizzes together this week?
No.
Okay.
No, we did not. I know there's some overlap. There's some overlap, but we're trying to make it in a planful way. I think it is good for you to hear the same things from different people using different words. But yes, I know this is one of the things that he's harping on, is if you can write a likelihood function, you can do anything. And you have to be able to write a likelihood function in order to do Bayes. But it is possible to use regular flavor ML within, say, M+, and estimate a model that has all different link functions that measure the same latent variable. You can do it. There's an article about that coming towards the middle of the semester, actually. So when we get into other response options, that section. All right, other questions? Moving right along. Number 2. What are the 3 untested assumptions we make when using coefficient alpha to indicate reliability? So when we are adding items together to form a sum, called a test score or a sum score, or when we average those items, same difference, what are we assuming if we compute an alpha? What's the big one? Unidimensionality. If you don't have that, nothing else makes sense. It does not make sense to talk about reliability for not one thing. Beyond unidimensionality, a stricter assumption, there's 2 more. What are we assuming about the quality of the items? They're equal. Yeah, equal discrimination, otherwise known as tau equivalence, otherwise known as a Roche model in IRT land, by the way. So I'm hitting that point deliberately, even though CFA that's not usually a thing, because I know what's coming, and it's all the same idea. The idea that each item is equally related to the latent trait. There's some recent papers showing that you can have that be off a little bit and alpha is reasonably close, but that's still under the auspices of unidimensionality, which is the big one. And then last but not least, what about the item response errors? Unrelated, yeah. So there's a word for that. Actually, it's a 2-word phrase. First word starts with an L. Second word starts with an I.
Local independence?
Local independence, yeah. Local independence you can also think of as conditional independence, meaning after conditioning on the latent trait, after accounting for the latent ability that caused someone to answer the questions the way they did, the E's for different items are supposed to be unrelated. Now, what if they're not? Got to add it to the model. So where we are ending up, an alternative to alpha, which is known as omega, relaxes the latter 2 assumptions. It still assumes unidimensionality, but it allows differences in item discrimination because you allow differences in the loadings as part of your factor model, and if there's any error covariances, they go into the denominator of the calculation. So those 2 latter restrictions can be bent, but they have to be accounted for in computing a reliability. Unidimensionality is the big one. So what are the 2 things then that go into alpha? And Zoomers, I'm watching the chat as well, not leaving you out.
The number of items and the average correlation?
Yep, number of items and the average inter-item correlation. So how do you make alpha better? What kind of items do you need? More. Or more correlated items. Because you can't just add any item without dragging down the inter-item correlation. But the number of items appears to be a bigger determinant than the correlation itself. You get enough, it'll look good. If alpha is bad, though, that's probably a sign that it's not good. You're not measuring one thing if alpha is bad, because your items need to be correlated before they can be plausibly indicate a latent trait. So yes, more items that are more correlated is how you fix alpha. Another thing related to this, just as an aside, there's another version of reliability called Spearman-Brown. That one is even stricter because it adds another constraint of equal error variances. So there are formulas by which you can anticipate how reliability would increase if you added items. That's the Spearman-Brown. That's an assumption of parallel items. Equal item discrimination, equal error variances. So another stricter version of that. Those are all testable things. And by the end of this unit, you will know how to test them. It boils down to likelihood ratio tests, model comparisons. Make all the loadings the same. If it fits worse, not tau equivalent, not equally discriminating. Make all the error variances the same. Fits worse, they're not the same either. Okay. And why does alpha have to assume unidimensionality? What's not part of the formula that matters?
Correlation? Covariance?
Average correlation is in there. ... Yeah, the spread or the variance around them. So there was an example in lecture 3 of 2 different scales. One had all of the responses correlated 0.3, and it was 10 items. Another had 6 items with 2 pockets. There were 2 sets of 3 in terms of the correlation, and both of them were an alpha of 0.81. So yeah, if it doesn't indicate variability in the correlations, then it can't indicate dimensionality. So if all of the assumptions hold, alpha is a reasonable way to approximate reliability of a sum score, but we can do better. And then the theme songs, last but not least. Okay. Any questions on any of those or things you want to talk about? Good so far? Mm-hmm. Good enough, anyway? All right, then I will shut this part down. And we'll head back to the slides that we couldn't see last time from my basement. Internet from campus, a wee bit stronger. So we were talking about identification last time, right? Maybe? I think we were. So the idea of identification, we have this latent factor that's imaginary. In order to make the math work, we have to give it a scale. Giving it a scale means that we have to tell it what the variance of the factor is, what the mean of the factor is, and then the model can help us figure out what any covariances should be. But a mean and a variance is a starting point for every factor. So your choices in identifying the model are depicted on this slide 22 here. Let me start. This is the picture that I didn't get that I wanted. So with respect to setting the scale for the factor variance, something got to be 1. Either you can set the factor variance as 1 directly. Just tell the program, make it 1. Don't try to find that number. Just make it 1. Make it means fix it. You will call that, it's called a fixed parameter. Not to be confused with a fixed effect, which is a constant that is estimated. And I know the names are terrible, and I'm sorry. But this is how people talk. So I'm going to say I fix the factor variance at 1. That's choice number 1. The alternative and the default in every SEM package that I know of is to instead fix an unstandardized factor loading for one of the items to 1 and estimate the factor variance. What will happen then is that the number the factor variance becomes is the amount of item 1 that is thought to be true score that's driven by its loading. So we will see in M+, how the numbers rearrange themselves to give us basically the same information on 2 different scales across the 2 versions of this on the top here. Or the 2 different columns, I should say, is what we're looking at here. Now, does it matter which loading you fix to 1? It does not. There's only one instance in which it will matter, and I have seen this happen to one student before. She had her model all set up, wouldn't converge. So there was a row of estimates, an error message, no standard errors, no p-values. Just, this is where I left off at the last iteration. Good luck, is basically what the software said. And it turned out the problem was, ... When will this break? When does it matter which one you pick?
When the correlation is 0?
Yeah, if it doesn't measure that factor. If the item doesn't measure the factor, then there is no true variance to pass up to the factor to become the factor variance. And that was what happened in her case, is that her marker item was not related to the rest of them. Other than that, it doesn't matter. So I prefer, when I'm initially looking at the properties of a scale, to do the factor variance equals 1, because then the standard deviation is 1. And then when I interpret what a loading means, a loading is the change in the item response for a 1-unit change in the factor predictor. So a 1-unit change refers to a difference of 1 standard deviation, where we're talking about differences between people, because these are, each person gets 1 factor score, 1 per factor. Okay, remember this from last time? Maybe? Is it good to go back over it? Yeah, okay. Lots of nods on that one. Yes, indeed. So, big picture, factors are imaginary. Once we nail down a mean and a variance, then the rest of the math works around that. So, the standardized solution, in terms of if we standardize the item responses, standardize the factor, it will be the same, regardless of which square you're in this picture. it's just you're defining what 1 means. Do you remember my analogy? What does 1 mean? Remember me singing happy birthday? Yeah, the key. Yeah. So as long as everybody agrees to be on this note for happy birthday, like that's 1. Or everybody want to sing up here is a 1. Like I can't do that either, but all the notes rearrange themselves relative to that point. So like the next note is 2 steps up. The note after that is 4 steps up, right? You don't have to know what the exact letter is that you're playing. You just have to know which key you're in, and then everything is relative to that. This works the same way. So as part of your write-up, as your description of your modeling process, this is one of the first sentences that you would write, is how you identified the model, so people know what 1 means. Now, what I see people screw up, this happens at least once a semester, so we'll see if this will be the first class ever to not have someone do this. What if I fix the factor variance to 1 and I fix the loading to 1? It's doubly specified. So what am I saying if the factor variance is 1 and the loading is 1? What am I saying about that item? Perfect. It's perfect. If the factor variance is 1 and the loading is 1, that's saying that the first item has no measurement error. So you won't get a message that you did something wrong or that it's unidentified, but you'll probably get worse fit to the extent that that item isn't perfect. So it's a double constraint. It's 1 more than you need. So to recap, to identify the variance of a factor, either set it to 1 or set one of its factor loadings to 1. But something got to be 1. Is 1 necessary or just any number that's not 0?
Any number.
Any number. So if I wanted to have my factor be on, say, the traditional standardized scale where 100 is the mean and 15 is a standard deviation, could I do that? Sure. I'd fix the variance to 225. And everything would rearrange itself as that is my new anchor point for where the model scale is. Doesn't matter, as long as it's not 0. If I fix the factor variance to 0, then you will get an unidentified model. You'll get errors, because there's nothing then to correlate with. It's a constant. Okay, how are we doing? That's only half the battle, though. There's 2 sides to every model. Model for the means, model for the variance, that's just the variance side. On the other side, the factor mean, you can either set it to 0 or you can have one of the intercepts be set to 0 instead. By far, the most common solution is factor mean equals 0. That is the default in every package. There are very few circumstances in which you would want to change that. The only one that I can think of is in longitudinal data where you want to see the factor mean grow over time. Then having one of the occasions have a factor mean of 0, but then having either an invariance constraint or having the others have an intercept of 0 so that the mean's estimated, something like that would be the only situation. Factor mean 0 or an intercept of 0, but not both. So that one tends to be not as problematic in terms of people messing things up, because what happens in these software packages is that all intercepts are estimated by default, factor means are set to 0 by default. So it does that part of the identification for you. So I will show you 3 out of these 4 possibilities in our Lavon code and in M+, just so you get a sense as to how the numbers move around, but the answers are still the same in terms of what information it's telling you. So, recapping, on the mean side, either factor mean is 0 or one of the intercepts is 0. On the variance side, either factor variance is 1 or one of the loadings is 1. Questions or any of that you want to hear again? Let's see, comment from the chat, equal discrimination and difficulty. Alpha doesn't say anything about difficulty. So I think that's probably a question from several minutes ago. Sorry about that. Equal discrimination is the big one. All right. So identifying a model, part of it is making sure each factor has a scale. The rest of it is making sure your model is solvable. That it can even work, and it boils down to how many indicators you have per factor. So that's the next part that we have to go over. So part 2 then, after scaling the factors, then we are trying to reproduce the item means and the variances and covariances across items using our model, and ideally using as few parameters as possible. So we will use maximum likelihood, regular flavor maximum likelihood with a robust correction in this class. By the way, REML is not a thing in SEM. To estimate the following parameters. So we have vocabulary here. Measurement model. When you hear that word, think item stuff. Measurement model is item intercepts, item factor loadings, and error variances across people per item. Structural model. When you hear that phrase, think factor stuff. Factor means, factor variances, factor covariances. Eventually, what we want to look at is how well our model parameters recreate those original item means, variances, and covariances, where close is good. We want to be as close as possible. But in order to even get to that point, we have to make sure that our model is identified, that we can even find all of the estimates by which to recreate those pieces of information. So this boils down to a couple of things. Degrees of freedom is one. So there are degrees of freedom here have to do with the number of variables. In every other class that I teach, degrees of freedom have something to do with people, not in this one. So when we're talking about a structural equation model, or a special case here, confirmatory factor analysis, we need to know how many items we have. The formula to figure out your total degrees of freedom based on the number of items, which is V, is V times V plus 1 divided by 2. Those of you from the longitudinal class will recognize that piece as the number of variances and covariances possible in an unstructured matrix. Plus V then adds the item means back in. So this formula right here gives you the total number of item means, variances, and covariances in your data set that we have to work with. Then we have to figure out, of that number of degrees of freedom, how many are we spending by estimating measurement and structural model parameters. So for instance, if I have 4 items, my total degrees of freedom are 14. I've got 4 means to recreate, 4 variances to recreate, and 6 possible covariances. So model degrees of freedom then is fundamentally the idea of leftover. How many did we not spend that we could have? It is conceptually analogous to what I would call denominator degrees of freedom in regression language, like how many more slopes could we add that we didn't? It's analogous to that, but it concerns the number of variables. So we have to have number of possible parameters left over be positive in order for your model to be identified, solvable, estimable. So when would it not be? Well, if you only have 1 or 2 per factor. So language, picking up more vocabulary words. The term under-identified means you are trying to estimate more parameters than you have pieces of information with which to estimate them. Under-identified is like an overdrawn bank account. You're spending money you don't have. So if I only have 2 indicators for a factor, this is not identified. This is not solvable. In terms of where the degrees of freedom go wrong, how many do I start with? I've got 5 possible because I've got 2 means, 2 variances, and I've got 1 covariance between the 2. 5 pieces of information. To estimate every parameter in this picture, I would either say I don't have any factor variances because I'm going to fix it to 1. I don't have any factor means because I'm going to fix the factor mean to 0, but then I'm going to estimate 1 loading for each variable, 1 intercept for each variable, and 1 error variance for each variable. 2 plus 2 plus 2 is, say it with me, 6. And how many do I have to start with? 5. So my degrees of freedom left over are -1. Not going to happen. So this is under-identified or not identified. And where the problem boils down to is the loadings. So if you think about what the job is of each of my parameters in terms of recreating the original data, the job of the intercepts, which are estimated, is to recreate the means. The job of the error variances is to recreate the total variances in the data. The job of the factor loadings is to recreate the covariances. That's where the problem comes in. Everything else has an even match. So I've got 2 loadings that are trying to recreate 1 covariance, and that's why this is broken. In your textbook, he gives an example that I liked. Let's solve this problem. What are x and y if their sum is 7? 1 and 6, 5 and 2, 3 and 4, 3.5 and 3.5. Right, there's an infinite number of solutions that'll work because you don't have enough information to solve the puzzle. So same way here. If the correlation between these two is 0.64, then here's all the things the loadings could be to make that work. So not identified means not solvable, do not pass, go, it's not going to work. But I only have 2 indicators and I need to make it work because I need to graduate. Or my grant is funded and I can't tell them that I can't estimate my model. What do I do instead? I set these 2 equal. Set the loadings equal. Then I've got 1 loading instead of 2 for 1 covariance. Then I'm trying to estimate 5 things with the 5 pieces of information. Degrees of freedom 0, copacetic. So equal loadings, though, corresponds to what am I saying about these 2 items? They're equal in what? Discrimination, equal in quality, you could say, equal in how well they relate to the trait. Now, is that likely to be true? I don't know, but I don't have enough information to find out. This is what I got to do. So the idea of using like test-retest reliability or parallel forms reliability in CTT, the reason that you have to put constraints on all of that to make it work is because of this. It's an under-identification problem. So you can have a factor with 2 indicators so long as you constrain the 2 loadings to be equal. So if I go through the left-hand column here and I tally up my parameters, then I would have a factor variance of 1 that's fixed, a factor mean of 0 that's fixed. I'd have 1 loading instead that's set equal across the 2. I'd still have 2 intercepts and I'd still have 2 error variances. Then it would work. By the way, a factor where all of the loadings going into, from it, I guess, if I'm saying this correctly, all of the loadings that go with it, if they're equal, that is called a random intercept factor specifically. And yes, that is the same random intercept that I talked about 2 hours ago. Not a coincidence. Because if you look at the different ways of identifying the model, if these loadings are equal, I could either force them to be the same estimated number and say the factor variance is 1. Or, because they have to be equal, I fix them both to 1 and let the factor variance be estimated. Does that sound familiar? Right? Like the U0 random intercept in the equation doesn't have any multipliers in front of it because there's a 1 that's as it's loading. The variance is estimated instead. So fixing loadings equal turns this into a random intercept factor specifically. It is a statement that both items are equally good. So in this situation, if you fit this factor model, essentially what you have done is taken the correlation between those 2 items and given it a name and put a circle around it. That's what the factor is whatever they have in common. That's it. Is it the thing you wanted to measure? Meh, that's a validity argument. But with only 2, you're kind of on shaky ground to say that. You're measuring anything. Whatever they have in common, that's what the factor variance is. Okay. With me so far? So don't do this. There's your take home. What about 3? 3 is just identified, meaning no parameters left over, you've spent them all. You're broke. Now, is it good to be broke? Well, it's better than being in debt, right? Like if these are my choices. There's a comedy routine that I saw one time talking about like someone who's overdrawn, and the person says like, I don't have no money. Like if you're overdrawn in your bank account, you don't have no money. You have less than no, less than 0. So if you're moving from being overdrawn to broke, that's an improvement. But broke is not desirable. And just as broke is not desirable, 3 items is not desirable. Because while this model is estimable, you've got enough information to figure out what all the parameters should be, it perfectly recreates the data. It is a rearrangement of the data you started with. It is not a prediction or a summary or a patterning. So if I have 3 indicators, I have 3 means, I have 3 variances, I have 3 covariances, 9 total. So if I fix my factor to mean 0, variance 1, then the 3 means that I started with are perfectly recreated by the 3 intercepts. The 3 variances that I started with are going to be perfectly recreated by the error variances because they'll become whatever is not the factor needed to get back to that right total. And the 3 covariances are going to be perfectly recreated by the 3 loadings. There's a 1-to-1 match on every possible part of the model. So it's not a model, it's a description. And to me, this is the bare minimum that you would want to do. The problem with not having any degrees of freedom left over is that you can't say you're right. You can't say that there is empirical support that these 3 items measure one thing. There is no other alternative. So in this situation, if you want to be able to say a 1-factor model fits these data, you'd be like, that's because it has to. You would want to look at the size of the loadings, though, as supplemental evidence as to whether or not 1 factor is plausible. If I had standardized loadings, which range from -1 to 1, and they were something like 0.8, 0.7, and 0.1, that model is going to fit perfectly, just as well as a model that was 0.8, 0.7, and 0.8. But the one that's 0.1 makes me kind of think that's not really the same thing. But you can't say that because you're out of degrees of freedom. So there's an appendix in one of the book chapters where he goes through the math as to how you can use the correlations between the items to figure out what the loadings have to be. So I will let you work through this on your own, but I thought this was useful as an illustrating point. 3 loadings, 3 correlations, even. Just identified. No degrees of freedom left over. So this is possible to estimate, but it's not a testable factor structure. If we're at 4, now we got something to work with. Now you have the chance to be wrong. So if we have 4, that's 14 pieces of information going in. If I say that the factor variance is 1 and the factor mean is 0, then the 4 intercepts perfectly recreate the 4 means. The 4 error variances perfectly recreate the 4 variances. The 4 loadings have to do the job of 6 covariances. That's where the 2 degrees of freedom comes from. Now you have a chance to be wrong. The loadings are predicting a pattern of relationship across the items that could be incorrect. So the extent to which that pattern of covariance that is implied by the model matches what's in the data, then you have a chance to test whether you're right, that these 4 things measure 1 factor in common. So the term for this is over-identified. It's backwards from how I would think about it in terms of banking, because you're not overdrawn. It means that you have more money in your account than 0. You have money left over. You have 2 monies left over, whatever parameters is. Or to damage, as my son would say, maybe. He talks about video games where damage is a singular noun, no matter how many you have. Does this sound right to anyone else? Can you confirm or deny? Like, this person has 57 damage, but I only had 13. I'm like, is that good? Damage would be bad. Or damage is, but no, it's just damage. So 2 whatevers, whatever units we're in, are left over. So this is not only estimable, meaning we can actually find the answers, but we can use those 2 degrees of freedom to test fit. We can be wrong. Okay. So even though this is allowing us now to estimate and test our one-factor model, do you think 4 items is enough? From a measurement reliability standpoint, would you be comfortable with a 4-item test deciding whether you get to be a lawyer or a doctor or a nurse or a CPA or anything else? No. Nah. So none of this conversation right now is about reliability. This conversation is not about how well we have measured the factor. This conversation is, can we measure the factor? Can we even get started? If the answer is 2 items, no. 3, yes, but just barely. 4, okay, now we're talking. 5, even better. So the more items you have, the more chances you have to be wrong. A stricter pattern is implied by this factor, having 1 factor. So people ask me when they're planning studies, how many items do I need? My answer, of course, is going to be more. But I would say, at a minimum, 5. Because then you have room to be wrong about 1 of them, if it doesn't work, and you've still got 4 left over. And if you're wrong about 2 of them, you've still got 3 to at least make it work. So 5 per factor is a reasonable starting point as to where you can even start this process, but it's not enough to guarantee reliability. Okay. How are we doing? So have you ever had someone tell me, it's not you, it's me? Here's the equivalent of that. Empirical under-identification. It's when you did everything right, but your model's still not identified. It's not you, it's your data. It's not your fault. So under-identification, you will get error messages that say things like not identified, under-identified. And you will be able to tell, even if you scroll past the error message, because you will get a column of parameter estimates with no standard errors and no test statistics. Because it will print out whatever its last guess was and be like, here you go. I don't know what to do with this. You figure it out. So once you've gone through the checklist here, does every factor have a mean and a variance? And does every factor have at least 3 items or constraints if you only have 2? Then there are a couple examples when you would still be under-identified, even though you've done everything right. Here's one of them. So each of these factors here is locally under-identified. Locally meaning just about that factor, not as the model as a whole. The only way that this model as a whole is going to be identified is if there is a covariance between the factors. If the covariance turns out to be 0, then they can't borrow information from each other, and each one has to stand on its own, and then we're back to each one only having 2. So this model, let's count up how many degrees of freedom it would have. What's degrees of freedom possible for 4 indicators? 4 means, 4 variances, and 6 covariances. 14. Okay. What all would we estimate? How many intercepts?
4.
4. How many means? 4. Even. How many error variances would we estimate? 4. How many variances are we trying to recreate? 4. Even. How many loadings would we estimate according to this picture? 2. How many factor variances would we then have to estimate according to this picture? 2. Yep. So we're at 4 terms, 2 variances and 2 loadings, and there's 6 covariances, so we're still okay, but then we have one more, the factor covariance. So how many parameters are left over that could possibly be added? How many degrees of freedom are left for our model? 1. That's it. 1. We've spent 13. I'll count them up again. What we've spent: 4 intercepts, 4 error variances, 4 loading/factor variances. 1, 2, 3, 4, and then 1 covariance. That's where the 13 comes from. 14 possible, we got 1 left over, just barely over-identified. So this will break if there is no covariance between the two. Likewise, this is what happened to my student, whose model was unidentified because she chose the wrong marker item. It wasn't related. So you would think that if you had 3 items, you'd be fine, but not if one of them doesn't work. Then you're back to the 2-item situation. And how do I fix this, by the way?
Equal discrimination.
I got to make these 2 loadings equal. That's how I would fix this. Then I'm down to 1 loading for the 1 covariance, and I'm good to go again. So there are situations in which you can do everything right and it can still not work. But to the extent that you have more than just the bare minimum number of indicators, that's less likely that you'll run into those. Yeah, all right. Making a decision is about where I want to go next here. Just a second. I think this might be a good time to start the example. But 2 more. Yeah, 2 more slides, 3 more slides, then we'll do that. Yeah. Then that's a good break. Okay. So all of the pictures that I've shown you so far, there is a name for this type of factor model where the factor is the predictor and it causes, like the arrows go out of the factor into the boxes. This is called a reflective model. The indicator responses are a reflection of the factor. The factor came first, and it is why the responses are supposed to be correlated. This picture says the E's are unrelated. The E's are unrelated because the reason that these boxes would have been correlated is up here in F1. F1 is the reason why these indicators were correlated. That's what this model is saying. This is reflective. The alternative is what's known as formative. Formative, not the same formative for teachers who give formative assessments. This is a different formative. I know. Emergent is another name. That one I think has fewer synonyms. But the question is which way the arrows go. So all of the rules that I just taught you about identification are for reflective models where the factor is the predictor and the responses are the outcomes. Alternatively, you can have something that looks like this. So this is an example of a formative factor where the boxes, the arrows go from the box to the factor. This is an example from your textbook. The idea is that chronic life stress is an amalgam of all the things that could cause stress, right? And we could make a list, like what's stressful about life? All the things. But if you have high stress because of this reason and that reason, it's not that those reasons would necessarily be correlated. Like people could have different reasons for high stress. There isn't something like on Earth that's like, I have stress ability and it's going to cause all my answers. Like it doesn't work that way. The idea behind this model is that stress is like the whole is greater than the sum of the parts. Like these things combine together, and if you have a lot of these, then you have a lot of stress. So in switching the direction of the arrows, you're making a different theoretical statement, but you're also making a very different mathematical statement. If the arrows go from the box into the factor is the outcome. The responses are the predictors. It is backwards in terms of which side is on the equal sign. And that means that the factor is no longer posited as the reason the items are correlated. There is no predicted correlation among the items because of the factor. The factor is just a separate latent outcome. And so they'd have to add all the correlations back in. So if I have 4 loadings here, one variance of this factor, which is called a disturbance, which means leftover factor variance for something that's been predicted. But I got the 10 correlations here and the 5 variances and the 5 means. I'm at -5 degrees of freedom. So on its own, formative constructs are not identified. The only way that you can possibly do this is to stick other stuff in the model. So this picture then is identified. This picture says there are 3 causes of life stress, which is this latent construct, and life stress in turn is measured by causes, the responses to X4 and X5. So this one is life stress, and now the model is identified because there is enough information to make all of the parameters work. But this is a different theoretical statement. In addition to stress, an example that I saw that works with this would be house prices. So what makes a house expensive? You don't have to own a house to answer this question. Location, size, newness, number of bedrooms, number of bathrooms, right? Like all of these things could be the boxes that cause house value, right? Not price, but value, which is ambiguous because it depends on who's buying the house and what they value it, how much they're willing to pay. Indicators of value then would be separate appraisals. You hire someone, they come to your house, they try to figure out what its value is, and that's their opinion. So the value of your house causes the appraisers to answer their questions in the way that they do. The things that cause the value are over here. So this is one of the things that in thinking about latent factors, does it even make sense to have a latent factor? Not for every construct. Some constructs do not lend themselves to reflective models. I can't remember if I had, I think I may have taken it off. I had an article about this on there, but if you ask the Google about formative measurement models or emergent measurement models, you will find discussions of this and how to make it identified. I will also draw a parallel that those of you who know principal components analysis, that's this. A component is an outcome, a factor is a predictor. So there is a direct parallel between what we think about as factor analysis, where the predictor is the factor driving the item responses, versus component analysis, where the responses are the predictors driving the factor as an outcome. Component as an outcome. You got to use different words because it means different things. So just a brief aside about that. So summary of what we've seen so far then. Big picture stuff. CFA, confirmatory factor analysis, that's what we're doing. It is a linear model. It specifies that a latent factor that is a continuous, unobserved thing predicts item responses that are supposed to be normally distributed in continuous variables. The goal of doing this is to test hypotheses about factor structure. Does this set of items measure one thing, or does it actually measure 2 things? Does this set of items measure this one thing equally well, or should there be differences among items in their discrimination via different loadings? Those kinds of questions are the purpose of doing this kind of analysis. From an explanatory point of view, we still don't know anything, though, because factors are latent. We don't know why some people have higher factor scores than others. We just think that they do. So we're partitioning the variability of these items into what is true score due to the factor, which is still technically error variance because it's differences between people that we don't know why, and then not the factor, which is what we call the error variance that's left over, which is everything else. And it could be error, it could be stuff the item measures that none of the other items do, which would be unique or specific, but we don't know. The parameters, the job is to recreate the item means, variances, and covariances. Intercepts, estimated, recreate means. Estimated error variances, recreate variances. Estimated loadings and factor covariances, recreate covariances. And you need at least 4 items to test it, at least 3 items to estimate it, and if you only have 2, you got to make constraints. All right. So one of the benefits of this approach that is not discussed in the literature enough is this idea of person-free and item-free, separation of persons and items. You get that in CFA. Because each item has separate characteristics, each person has separate characteristics, and in theory, so long as you have the overlap, you can compare latent factor scores of people who receive different items. The key is that they all have to be measured along the same latent continuum. So not everybody has to answer every question, and that gives you tremendous flexibility. That's sort of the baseline of where like adaptive testing would start. In this context, adaptive testing would proceed by giving people items that have stronger loadings, because this framework doesn't pay attention to difficulty. It assumes that if an item is good, it's equally good. But in order to have different possible responses, we have to break the tie between the people and the items. So we're not using sum scores to accomplish that. All right, 256. All right, we are not talking about estimation today. Decidedly not. But this is my joke, though. Have you heard of the term black box? Like to describe something that you don't know how it came from? What's funny to me is that when you run M+, a black box literally pops up on the screen, like fulfilling the metaphor. It is a DOS window. For those of you who've never seen one before, that used to be how computers were run. So that's what we get to talk about next time. But I think it would be instructive to start talking about software. Can we do that with the little bit of time we have left? Let's do that. I've got example 4 here. So this is the handout that I built. It has a whole bunch of code and a whole bunch of output across programs. The full original files that all of these pieces came from are in the zip folder, but not the data because these are real data. So these real data are part of a publication that is my most cited article in my entire Google Scholar portfolio. And I am 3rd author on this paper. The 2nd author is dead. The 1st author is no longer in academia, which means I get at least 3 emails a week from people who want permission to give the forgiveness scale. Let me tell the internet, are you listening? Use the scale. It is publicly available. It is fine. You do not need my permission. It's fine. The items are in the publication. There is a website called like heartlandforgivenessScale.com or some shit like that. Go there. You can find everything you need. You do not need to email me for permission. Okay? Just putting that out there.
TLDR, don't email me.
Exactly. Too long, didn't hear. Don't email me for permission about the forgiveness scale. It's out there. But it's a thing. I answer like at least 3 times a week I get these questions. But anyway, the backstory of this. So I was a graduate student on this project. The creators of the scale, so Laura Yamuri Thompson and Rick Snyder, I believe is the deceased 2nd author who was her advisor, they wanted to measure forgiveness, but every scale out there only had references to either self-forgiveness or other forgiveness or God, and they wanted to add another dimension, which they called forgiveness of situations. Here are the items that made the final cut of the scale, so you get a chance as to how you can forgive a situation. I would call this the shit happens scale. Like, these are just bad things that happen to you, and you don't have anyone to be mad at, right? If a tornado knocks your house down, that's terrible, but, like, who are you going to forgive? So this is thought to measure, like, how do you respond to things that are out of your control? Do you ruminate or do you forgive, and that kind of stuff. And in the review process for these data, we had reviewers who argued just theoretically, I don't think you can forgive a situation, so I'm going to reject your paper. I'm not kidding. Like, that's literally what their comment said. It was like 3 sentences, and it got bounced. And so eventually it got published, and I chose the forgiveness subscale of this for my example because you can forgive a situation, damn it, and I can prove it. Because math don't care. Now, whether forgiveness is different than other constructs, that's a whole validity thing, and you can read the rest of the article. But this is just the CFA part of these 6 items specifically. And when I was brought into the project was because they had already done what they thought was an exploratory factor analysis, but actually turned out to be a component analysis, because that's what SPSS defaults to when you select factor analysis. It is not factor analysis. And they had submitted a paper for publication, and the reviewer said, well, that's nice, but I want a confirmatory factor analysis. So they wrote an ad to get graduate students who knew how to do this, and I applied, and I was like, I learned how to run EQS for 10 minutes. Can I do this? And they're like, sure, go ahead. So I learned a lot in playing with these data. It's a long story, but it's part of my past and still my present. Don't email me. It's fine. You can use the scale. So these are data from what we used to call mass testing, which is that still a thing, psych people? Do we have mass testing at this university? Basically, at the beginning of the semester, because all of the psychology intro students have to do research credits, mass testing is where they all take a bunch of screener tests so that people can follow up with them to select them for more specific inclusion criteria. But you can each lab basically got to add so many items to this mass test battery. And so it was 18 items in total, 6 measuring self, 6 measuring other, and 6 measuring forgiveness. So here are the items. I have noted that 3 of them are reverse coded. So they're not actually measuring forgiveness. They're measuring lack of unforgiveness. That's the best version of English, is put a label on it. So if I am disappointed by uncontrollable, I continue to think negatively about them. So I might call that rumination, maybe, but I'm told that that is a separate construct. I'm not a personality psychologist, so I'm not going to argue that point. But right off the bat, I want to highlight this 3 reverse coded thing because this is going to be a salient feature of the data. Here are the response anchors. So they used a 7-point scale in which 1 is almost always false, 2 is meh, because it was unlabeled, 3 is more often false, 4 is meh, 5 is more often true, 6 is, say it with me, meh, and 7 is almost always true. Not my call. This is how it was. Now, what would I say about this? If you don't know what to call it, what are they supposed to say it for means? So here's the correlation matrix of these 6 items. So this will be the first thing that I ask you to do with your data, because this is informative. If the items aren't correlated, then what happens? Game over. The purpose of a factor is to predict, to recreate, to say this is why the items are related, is because they're all measures of this one common thing. If the items are not related, they can't possibly be measuring one common thing. So these are at least positive correlations. Everything's been reverse coded. But as highlighted by the red and the blue here, there's a pattern to them. The red correlations are among the positively worded items that measure forgiveness, and the blue correlations are among the negatively. And the ones that aren't colored are across the 2. So just staring at this matrix, I will tell you, it looks like this is 2 factors. And it is going to be 2 factors. I'm going to spoil the surprise. 32 pages later, this is 2 factors. But I knew that from just looking at this. And you can tell these things too. Sometimes it's harder to tell, but in this case, there's a pretty strong signal. So I have the observed correlation matrix and the means and the variances. And just judging by the means, it looks like there's a chance that these things could be reasonably symmetric. The means are between 4 and 5, but the scale goes up to 7. The variances do differ quite a bit across items. And if you are reading an article that only gives you this much information, you can actually still do a data analysis using their data. Did you know that? If you are willing to assume that your item responses are normally distributed, multivariate normal, then this is sufficient statistics to do a confirmatory factor analysis. Every program will let you input either a correlation or a covariance matrix as data. So you can take other people's published articles and reanalyze their data if they give you a matrix. here's the covariance matrix. So in terms of what the model is going to try to do, it's going to try to recreate these 6 means. It's going to try to recreate these 6 variances, and it's going to try to recreate all of the covariances among these 6 items. That's the data going in. I have the conversion formulas for you in case you forget those, how to get from a correlation to a covariance or back and forth. You only need one or the other if you have the means and variances. No mass testing anymore, I hear. Well, I suppose that's more fair for the undergrads, but not so much for all the psychology people who need data. But here's the distributions of these things. Now, do these look normal enough to you? But I thought that if I had at least 5 options, I can pretend it's normal. It depends on how to use the options. So we have what looks like somewhat of a ceiling effect. These are after being reverse coded. Everybody wants to be forgiving. So whether this people are being honest or whether they feel like they should say that they're forgiving, I don't know. But I can't know that from this analysis. So I will show you some diagnostics that you can pay attention to answer the question, is this normal enough? There's not really a significance test, but there are things you can look at. And the first thing is this. Now, regularly, or I would say normally, but that's actually a pun, I would say that the marginal distributions don't tell us anything because all of the assumptions about our model are about residuals, right? The residuals are supposed to be normal. But in this context, if the only thing that is predicting these item responses is a latent factor that's supposed to be normal, and the E's are supposed to be normal, when you put the normals together, that's a normal. So marginally, your item responses should be normally distributed for this model to be appropriate. Where it's going to break down is in trying to predict item responses. If most of the data is on one side or the other, that's going to take the line and kind of force it like one way, so where it's going to go out of bounds. So what's going to happen is that it's going to want to predict item responses above 7 as the factor increases. And that can't happen. So what the model actually predicts when we're all done is going to be one of the things we look at to decide, is this normal and continuous enough, or are we going to run into boundary problems, in which case we want to switch over to IRT or IFA. IRT and IRFA are the same things with 2 different versions of the model. It's like saying 6 of one, half dozen of the other. All right. I think that's all I wanted to say about that. Okay, welcome to M+. So here's the story with M+. I understand and respect the fact that a lot of you are going to want to learn R, Lavon, and I'm cool with that. However, I would like for you to learn M+ also. M+ is very easy to use. Every single one of you should have free access to the full version inside the University of Iowa virtual desktop. I sent the people a list of all your names, and you should have access. So this is something that does more than what R can do. There are certain combinations of models we'll talk about this semester that are not available in R. For instance, the MERT package in R, in which you can do item response models using full information, doesn't have an SEM component. There's no way to talk about how to make one trait predict another trait. There's no structural model to it. And plus, you can do that. Likewise, you would not be able to do counts or any other kinds of generalized outcomes if you're using Lavon. It doesn't have it. So there are certain things that Lavon is fine for, and most of this handout, that is true, but as we move on, that won't be true. So I would like for you to get some practice using M+. What you do with your own data for projects is fine. And so for that reason, I've added R code to this, but I do want to emphasize M+ as the primary package. Fair? And that's because it's really easy. So all of the models that we're going to look at have this part here as a common entry point. So each syntax file for M+, you have to tell it where your data are, what they are, what variables you're going to use, what estimation options you want, and then you specify what your model looks like. So for every single model in this handout, this part would come first. I'm just not going to repeat it every single time because it would be redundant. All right. So we have title. That's something you choose. Data, this right here, .csv, do you know what that stands for? Comma separated values, text files. M+ does not take regular data files, it only takes text. .dat or .csv, which means that's the first step when you do an analysis, is to make sure that you read your data in. And it is a CSV file with no names at the top, only data. That is because the first thing you'll have to tell it, beyond what the name of your data set is what's in the columns. That's why I have this names option here, which is listing in order every single variable that's in this particular data file, which includes person ID, the 6 items that are measuring forgiveness of self, the 6 items that are measuring forgiveness of other, the 6 that we're going to play with measuring forgiveness of situations, and some scores that were already computed as part of the file. So we're almost out of time. This is a good place to end on. This is something I see at least once a semester too. Someone emails me an error message that's like, M+ won't take it. I don't know what happened. If the names are at the top of the file, that's what happened. The error message that it generates is not helpful in troubleshooting that particular error, but that is one thing you will see. The other thing that I have seen, and why I want you to practice with M+, following along with the video that I recorded if you can, is that for some of you this code will work, and for some of you it won't. I learned this the hard way 2 years ago. It has to do with the virtual desktop. For some people, they were able to just tell it what the file is, so long as this syntax file is in the same physical folder as the data set. And other folks, it threw an error and they had to write out the full path. So in the online version of this file, I have both in there, so you can try the shorter one, and if that doesn't work, then you can plug your path in. So those are the things that trick people up before we even get to the models that I wanted to make a point about. Question?
Do you have publicly available data? Can we pull this file from online?
You should be able to, so long as you take the names out of the top. Because you end up having to list them all, though, I would recommend cutting it down to just the items so you don't have to type forever and ever. And it doesn't know what the columns used to be called, so you can rename them. And here's another piece. Each of these names has to be 8 characters or less. It's 1985 up in here. That's what's happening. They have put all of their effort into developing the estimation and none of it into the front end or the back end. So that it's fair. That you just have to know that and have to accept it. So, all right. Any questions before we call it a day? All right, then. It is Tuesday, which means I say, see you Thursday, office hours tomorrow. Let me know if you need anything, okay? All right. Thanks for being here. Bye for now.